vortices perpendicular to the plane. On this side, this is the usual formulation in terms of indeed vortices. You have an equivalent formulation in terms of a plane without vortices with punctures in that case. So the wave function, when it goes around a vortex, has a non-trivial phase. It's a multi-valued wave function here. And here it's the regular wave function with an interacting particle coupled to Aharonov-Bohm vortices. So I will use this formulation, this interacting formulation with regular wave functions. So the problem is, again, one particle coupled to n Aharonov-Bohm vortices. Each vortex carries a flux phi, and the position of the vortices is R1 prime, etc., up to Rn prime. So we have n vortices. So what are the important parameters in this problem? Alpha, which is here. So alpha, what it is the ratio of the flux phi to the quantum of flux of the particle. For obvious reason that you probably know, the system is periodic of period 1, 0 and 1. Alpha equals 0, alpha equals 1 is the same thing. So we can always reduce the interval of alpha to 0, 1. And we can even reduce further to 0, 1 half because you interpolate symmetrically between 0 and 1 half on the one hand and 1 half and 1 on the other hand. 0 and 1 is the same thing, right? So we can always restrict ourselves to this interval 0, 1 half. So small alpha means close to 0. Big alpha means close to 1 half. So the Hamiltonian is here. So this is the standard. This is
the same alpha in both terms?
Sorry? Yes, I will explain this. So the Hamiltonian here is the standard Hamiltonian, Aharonov-Bohm Hamiltonian. K here is the unit vector perpendicular to the plane. Again, the R prime, the Ri prime are the location of vortices. I have one particle, its position is R, coupled to these n vortices. And as you mentioned, there is also this term here, which is needed to have a well-defined model with a correct short distance behavior at the location of the impurities. And of course, here alpha is the same, but understood again already to be in the interval 0, 1. Right, so these two alpha are the same, but we are already in the interval 0, 1, and in fact 0, 1 half in that case. The last thing I wanted to say, to simply give you the general definition of a model, is that the case n equal 1 is obviously the standard Aharonov-Bohm problem, which was introduced in 1959. Okay, so now, if you consider this problem as it is a very difficult problem, and we have, of course, to simplify it. So one way to simplify is to consider now that the position of the vortices are random, and we are going to average over the disorder. So this is going to introduce a huge simplification. So this is indeed the random magnetic impurity model. Magnetic impurity means random Aharonov-Bohm vortices, which was introduced, as I said before, in the context of the quantum Hall effect, because we have indeed a disordered magnetic field in 2 dimensions. So this is, of course, relevant for the quantum Hall effect. So what is the definition, the more precise definition of a disorder? We simply consider a very simple disorder, which is a Poissonian distribution. So here, V, this parameter V here is the volume in 2 dimensions, so it means the surface of the plane. Rho, which is here, is the density of impurity. So we consider the thermodynamic limit where V and N goes to infinity, and in such a way that the density, the impurity density is fixed. It's called Rho. So Rho is this parameter here. Here it's typically a Poisson distribution. And here what we say is that the vortices are uniformly distributed on the plane. Right? So the density probability is simply totally uniform on the plane with this, this term here for each of this Aharonov-Bohm vortex. So if you do the average of a disorder, you are going to reduce the number of parameters. At the end of the day, you will get only 2 parameters, rho and alpha. So we have simplified a lot the problem. There is no more position of vortices that have been averaged out. And of course, n also has been averaged out. So we have only at the end of the day 2 parameters, rho and alpha. It's still a difficult problem, but at least we can say something. So the first question you might ask is there a mean magnetic field in this model? If such a field exists, so I call it B average, it should be such that its flux through the plane is equal to the number of flux we have. So BV equal N phi, which means that B is rho times alpha phi 0. So basically B is rho alpha. So the question we ask is there a regime where this field, this mean magnetic field, is relevant? We can use a semi-classical argument for that. If you consider in a semi-classical picture what is the typical size of a cyclotron orbit in this mean magnetic field, so this is the Lorentz force, EVB equals V square over R. So we see that at fixed velocity, V, and rho being given, R is 1 over B, which means 1 over rho alpha. So now imagine that rho is fixed, the density is fixed. Here I have a typical cyclotron orbit, the density is fixed. You see that if I make alpha smaller and smaller, the radius is going to increase. So a typical cyclotron orbit will enclose more and more flux, and the mean magnetic field picture will be better and better. So we expect indeed to see a mean magnetic field when alpha is small, which means close to 0. And this is indeed what happens. So this is numerical simulation, which has been made in the original paper for the density of state, for the average density of state. So you see that when alpha is small, here it's 0.01. We see Landau level oscillation for the density of state, and the Landau peaks are precisely the Landau levels for the mean magnetic field. And when you increase alpha, 0.15, 0.35, the Landau level oscillation disappears, and here there is no more Landau level oscillation. So we interpret this regime here as a regime of strong disorder, whereas here it's a regime where you have an order and you see a mean magnetic field. So the question we might ask is why the transition between no disorder or small disorder and big disorder is around alpha equal 0.3. So to answer this question, we have to consider the density of state or the partition function, which is the same object, up to a Laplace transform. So we consider the average partition function, which is given by this. Remember the Poisson distribution, and where Zn is simply the average partition function in the n impurity problem. And in fact, you can reorganize this expansion here of average Z as an impurity density expansion where what appears is rho. So you have rho here, rho square, rho cube, and in front of rho I have the 1 impurity problem. Here I have the 2 impurity problem, the 3 impurity problem, etc. And I forget to say that Z0 is the free partition function in 2 dimensions, which scale like the volume of the plane. So what do we have? What do we know? At order rho, which is the 1 impurity problem, which is nothing but the Aharonov-Bohm problem, everything is known. We have a spectrum, so we can compute everything. And this is what we get here. This is this result here. So Z1, which is the 1 impurity partition function, divided by the free partition function, which is given here again, minus 1 is given by this. So, and if you would consider this term minus 1 over 2 times alpha here, which appears here, if you multiply it by rho, you get exactly what you need to build this mean magnetic field partition function I was talking about before. Right? So it is not surprising that this minus 1 over 2 here alpha times rho is exactly what you need to build what you know you should have. It means it is a mean magnetic field. Plus, of course, correction, which are due to disorder. So the leading term here is well understood. So it is the 1 impurity problem, again, which is totally known, and we can do exact computation. Now, here appears the 2 impurity problem already. So here I have 2 impurity, rho square. At order rho square, which is again the 2 impurity problem, nothing is known, basically. So we have to do perturbative computation. Again, the only thing that we can guess is it's this 1 over 6 here, because I have rho square here. So rho square alpha square is, again, a mean magnetic field term. It's rho alpha square. Rho alpha is the mean magnetic field. And we know that from the Landau partition function that it should be 1 over 6. So this term is known, but this is not known, this is not known. We have to compute it in a perturbative way, by perturbative expansion. So again, if I want to insist on this question, why alpha around 0.3, where we see this change of regime between lambda oscillation and no lambda oscillation, small disorder, strong disorder, again, we have to look at this object, but more precisely, we have to look to the log of z, which is related to the specific it. So I have no time to explain this, but from this information on log of z, we can guess the value of alpha at which there is this transition. And in fact, what we have to compare is this one impurity problem square and the two impurity problem. When these two objects are equal, this is a sign that the transition between no small disorder and strong disorder is taking place. So again, I told you that we know exactly Z1 over Z0 minus 1, which is given by this. Now we have to compute this thing here, right? Because we know only this term for Z2. So let me do that. We have to go, in fact, to fourth order in alpha to get a precise information. Going to fourth order in alpha means that I have, if you think to this as the particle loop, if there are two impurities, so one is here, it interacts twice here with the loop, and one is there, which interacts twice with the loop. So it gives you this rho square alpha 4 term. So we do this computation, we did this computation, and we obtain this result here. So now if I compare again this and this, taking this information up to order alpha 4, it is sufficient to get alpha equal 0.3. Okay, so we can understand by this type of computation, again, why this transition between lambda level oscillation and no lambda level oscillation takes place around 0.3, let's say. We have this information from the knowledge of these two terms here. This one, so this one was 0 here, and now this one here is given here. Okay, so far so good for what we did 10 years ago. Now, in the last 5 minutes, I would like to spend 5 minutes to tell you what we have done more recently, and which might be interesting now in the context of number theory. So we are leaving the quantum Hall effect, and now we are going to number theory. So what we have just obtained, as I said, is rho square alpha 4 equal, I put here quotation mark, 1 plus zeta of 3. That's what we obtained, right? This one was a fraction. In front of zeta of 3, there was also a fraction, a rational number. But basically, rho square alpha 4 is a linear combination of 1 and zeta of 3. This is not surprising a priori, because it is well known in quantum field theory, QED, QCD, etc., that if you do perturbative analysis, Feynman diagrams should be expressed in terms of zeta functions. And the general idea is that a given Feynman diagram has a topological structure, which might be complicated, and from the topological structure, you can guess that you should find, if you compute it, something which depends on zeta of n. So in fact, I am talking about multiple zeta values, and more generally Euler sums, which are generalization of zeta of n, with the same total n. So here, it's a little bit complicated. You have k1, n1, k2, n2, etc. The sum of the n is n1 plus n2 plus np is n, right? So this object, which is called an Euler sum, is in the family of zeta of n. And so every Feynman diagram with a given topological structure that you can guess by some kind of argument should be expressed in terms of this Euler sum with n1 plus n2 plus np equal n. Okay? So here, what we obtain in our problem, this two impurity random Aharonov-Bohm problem, we obtain that this Feynman diagram I was considering is 1 plus zeta of 3, and in fact, we were able to re-express it in that way. So here we have a simple integral over a product of Bessel functions. K0 and K1 are modified Bessel functions. And you see that the total weight here is 2 plus 2 equals 4. So 2 plus 2 equals 4 is associated to zeta of 3. So what we did in the last 2 years was to compute what happens here, what happens at order alpha 5, alpha 6, etc., to see if this structure in terms of zeta of 3, zeta of 4 will continue to be valid. I'm sorry. So what about the dots? So rho 2 alpha 5, which is the next order, is in fact trivial. Rho 2 alpha 6 we wanted to compute this object. So this is now the Feynman diagram which is contributing. And this is difficult computation, but we could do it. And we found this result. This Feynman diagram, which is order rho square alpha 6, is again expressed in terms of Bessel function. Now you have a weight 6. So you remember that before 2 plus 2 was 4 for zeta of 3. So now we are at order alpha 6. We have 6 here. So we expect zeta of 5. And indeed, there is also a term which depends on zeta of 5 here. Okay, so the structure seems simple. If you compute in this random Aharonov-Bohm problem for 2 impurities, if you compute Feynman diagram, you will get, at any order, integral on Bessel functions with a weight which is n plus 1 with respect to the zeta you might expect here. So here it's zeta of 5, and you have weight 6 here. Now, what was very surprising is that when we realized that these Bessel integrals are not, in fact, expressed in terms of Euler sums of the type zeta of 5. So there are different objects. There are new objects which are not related to zeta of 5 or Euler sums related to zeta of 5. So this is a little bit surprising because, again, if you look at this perturbative result, these 2 objects are on the same footing as zeta of 5, but they are different from zeta of 5. Okay? So this is the main thing that we got. I have 1 minute, maybe? So just to finish, in 1 minute, you can play with these integrals. So you can define new family of integrals in terms of Bessel functions. So you see you have k0 power p, k1 power q with p plus q. So the weight is p plus q. And at each weight, so p plus q equals 4, this is a thing we have already discussed. You have, in fact, 2 basic objects here. For this weight, you will get 3 of them. For weight 6, you will get, again, 3 of them. This is the basis on which you can express all this family of integrals. Okay, so I have no time to say much more than that. Let me conclude by saying that in all this family, you can select the most simple integral that you found. So this one here, uk04, uk05, uk06. So in general, we can introduce this class of integrals, right? uk0 power n plus 1. We know that they are related to zeta of n, but they are not in the category zeta of n. Again, they are different. They are not. We cannot express them as linear combination with rational coefficient of Euler sums, which will be of the type zeta of n. So they are different objects in number theory. And so again, okay, I'm finishing now. So interesting properties to study, certainly. Interesting in number theory. And what is remarkable is that they are, again, coming from an Aharonov-Bohm problem. Okay, and this is here the references if you are interested. Thank you. Yes.
Can you repeat the question?
So the question is the statement that these integrals are not linear combination of Euler sums of weight n is indeed, you're right, a numerical statement. So we can go to very high precision and we are totally sure that it is not a linear combination, but you're right to say it's simply a numerical statement. It's not an exact statement, of course.
Any other questions?
How it has, what it has to do, if it all has to do with the giant magnetic resistance, you know.
So the question is, has this something to do with the giant magnetic resistance?
Yeah, because I see your first reference is 95.
Yes.
There was a work by a guy named Nielsen, some few other guys. You know.
Yes.
They studied the problem which was posed in the 70s by Yoichiro Nobel Prize winner of last year. He called this Aharonov-Bohm medium. You know, this is a kind of disordering medium,
yes,
which is supposed to help explain quark confinement. So this was the idea of Nambu.
Yes.
And then, of course, if you do this for some monabelian gauge groups, which have the usual abelian subgroups, basically what is this? How it works is basically that you saturate the path integral by abelian configurations. Meaning, it's all basically usual Aharonov-Bohm mediums. Anyway, so
The question is that
the
if
question is what your work has to do with random magnetic impurities and so on.
has to do with this model, I don't know because I don't know this model.
No, with a giant magnetic resonance.
Giant magnetic resonance, I don't know either. I'm not sure there is a relation.
It was a very interesting phenomenon.
Maybe you could tell me the references, we can discuss that. But I'm not aware of that personally.
I was interested in the problem because I'm interested in problem.
Okay.
Okay. With that, let's thank you.
Okay, thank you.